Hi, I'm proud to present the results of my hobby, logarithmic pole model. I've been working on this since about year 2000. My name is Petri Muinonen. I was graduated in astronomy from University of Oulu, Finland in 1990s. In a brief summary of the contents, first we go through the objectives of the model of the couple of slides and show the constituents positive logarithmic pole and negative logarithmic pole called PIT and NIT and their interactions. Then there's this large-scale introduction to Big Bang scenario, inflation and its end, that is naturally arising from the model, and the emergence of 3D brane at zero potential of the system at system level. Then we calculate the speed of light along the 3D brane and go through the luminal aggregates, photon, that is the dipole of logarithmic poles, and the neutrinos, and also see what's the reason for the neutrino oscillation. Then we go through more complex pole aggregates that are particles bound to the 3D brane, and extract for them function of acceleration as a 3D distance that converges to the Coulombic one. And then we see how this what is coupling of different kind of aggregates to this potential here. So we can attribute the charges to fermions and quarks. And then we extract the similar function also to the Newtonian acceleration. That's like it's converging towards the Newtonian one in 3D, only attractive potential acceleration, and then go through the mass table for several particles by fixing just one mass. It could be equally either Higgs boson or, for instance, neutron. Before even going to the objectives of the model, I just quickly show you this slide. This is about mass construction for various aggregates that the model contains, and this shows that the mass is determined by factorials based on number of poles, logarithmic poles within the model. Now, this is something rather significant, since present model of particle physics, or the standard model, there is this Higgs at the bottom. Yeah, it is the most massive, and other particles are coupled to it, but the coupling constants are put in practically from experiment, and it is Higgs is just a kind of justification that this kind of origin of mass is justified. Now, this model actually gives a way of calculating first order value for those masses of particles, and this is something truly new. The intent of this model has been to test the hypothesis over a single potential function that would offer structural rigidity to matter, also offer singular behavior in certain conditions, through a counteraction of inherent repulsive and attractive domains within this function. And this is an alternative to such an approach where you have various separate interactions and their interplay with numerous quantum rules ad hoc to prevent collapse of the matter either into singularity or dispersion to infinite distance. And then we have selected this logarithmic potential to test and a scheme of logarithmic poles, and therefore the interactions is extracted from this, and we derived stable pole aggregates and obtain particle-like properties such as charge and mass from that. And then we model also the system in large scale and identify a zero potential at system level as a candidate for observable universe like 3D brane embedded in the system. Since 3D brane is obtained as a candidate for the universe, one must ascertain that we get a physics that is conformal to the one we observe actually in our physical environment. So first of all, in the 3D brane we'll have the speed of light. Fortunately, we are able to calculate the speed of light from first principle of the model for any positive pole that is whose trajectory is along the 3D brane. And the model in itself is non-local, but we obtain locality through this limited speed of propagation for positive poles along the brane. Then we got also a distinct subset of pole aggregates that are luminal particles which only have one positive pole in them. We have to certainly find out how to obtain the accelerations of classical physics that are inversely proportional to the r to the second power, where the r is the 3 distance. It's the second order kinematics from the model give the dipole accelerations that have this property, very useful property. And we describe the aggregates, pole aggregates couplings, charge and mass to these second order kinematics accelerations that are two different accelerations. One is has both positive and negative value, and the other with some algebraic tricks we get it only to have the attractive component to it. And then we also just want to underline that this first iteration of the model is a kind of version 1.0, and well, it has only one free parameter, that is the number of the poles in the system. We now look in more detail into the attraction and repulsion rules between poles. The amplitude of acceleration along the line joining the poles is always 1 over d, where d is the 4 distance between poles, and it is also a derivative of a natural logarithm. And a pit pair has attraction at all distances. At 0 distance there is a switch of identity of poles and they just go forth and the kinematics can go on. while for a knit couple there is a repulsion at any distance. The particular case is knit pit dipole, where there is an attraction at distances larger than unit distance, and there is a repulsion at shorter distances. This oscillation is around symmetrically around the zero potential that is formed by the dipole itself, and it is positioned like this. In between, it is transverse at right angles to the axis of the dipole, and this is also the plane into which the dipole is aligned with the 3D brane of the system at zero potential. Here we see on the left hand side three functions, as there are functions of 4 distance between poles. The first one for pit-pit pair, then for a pit-knit dipole, and for the knit-knit pair. In which instead we have on the right hand side the accelerations caused by these potentials, and we can see that there is when we are below the horizontal line here, it means that there is a negative acceleration, so it means that it is an attractive acceleration, and on the opposite, then on the positive side, we are talking about the repulsion. And what is particular here is that there is first there is a potential well at unity for pit-knit pair, and also there is this discontinuity caused by this acceleration, or rather that there's a kind of cusp in the function. So discontinuity in acceleration, and this probably has implications of causality of kinematics taking place under this function. It is noteworthy that this pit-knit dipole, the rules of interaction presented on the previous slide, they are very concisely described by the potential function of absolute value of logarithm of 4 distance. This schematic cross section of the 4D system at the origin, we have the coalesced pits at the center because of their mutual attraction, and this snapshot is right after the inflationary phase of the system expansion. This is because within the 0.5 radius 4 sphere, in the beginning we have all the pole pairs that are mostly repulsive, 3/4 of them, and afterwards, when knits are propelled outwards, it means that beyond the unity distance from the core of the system, the attraction kicks in, so it changes the overall situation so that we have 3/4 of all pairwise interactions at the system level that are attractive. There is inertia of those blue knits going outwards, so it means that the system is still going to expand, and we will also show that there is only minimum amount of tangential velocity needed to keep them on an orbit indefinitely. Also, some positive poles, some bits are tugged and pushed outwards with the knit cloud, and those are actually constituents of the ordinary matter along the 3D brane that we see here depicted in very early on as a yellow dashed line, and very at this stage probably it's not very spherical. Actually, there might be also various bubbles of zero brane here, but they are then coalescing together, disrupted to melt into a continuous system-wide zero brane. Here we can see some results produced through numerical calculus on the initial situation of 4D system, where there are nits that are shown here as a kind of cloud that is in expansion by the repulsion of both pits that are shown here, very close to the center. Is the origin of the 4D system, and the radius is increasing towards the right hand side of the graph. And nits are propelled outwards, and this is continuing, especially powerful until they reach unit distance from the pit center here. Since after reaching that distance, there begin to be also the acceleration inwards. You can see here there is the acceleration inwards of the nits, but then they also have inertia outwards caused by the slide from this early potential peak, and so you can see that the accelerations here very near to the origin are much higher than the acceleration inwards at this point. So it means that the knit cloud is going to be expanded, and it is also so that some of the pits are propelled outwards both by pushing of nits that happen to be just inside in an orbit inside of some of those bits, and then also by kind of attraction of this expanding cloud here. This is something that will have to be simulated dynamically and seen more thoroughly later on, but this gives an idea that we have actually possibility to extract some of these pits to form ordinary matter then along the zero brane at this zero brane that is an expanding 3 shell around the 4D origin of the system. This is a very schematic picture of the later situation or later evolution of the 4D system, where most of the pits, at least I'd say more than 95% of bits, are concentrated at the center of the system, and a few percent are on these 3D zero brane here that's surrounding the center. And it means also that most probably the proportion of nits to pits over along this 3D brane, it is something like 20 to 1 or something like that. So there are much more needs in this space. And what we wish to show here is that what is practically the proportion of the system that we perceive as a visible universe. It is probably something like this enhanced area here. It means that we will gain messages or particles, I mean photons, that arrive from that part of the whole of the universe. And this 3 shell is always in expansion. But now we are mostly interested in what is keeping the pits on this shell. So pits have, at unity distance from them, as do nits, they have zero potential, and that zero potential is keeping pace with the expansion of the system's zero potential. So pits are positioned very close by to this brane, and while they are there, it means that we know from also physics physics classes that there is this thing called centrifugal force, or acceleration rather, and it is v squared over r, in this case d, since we are talking about 4 distance and 4 radius. So the acceleration from centrifugal causes is this, and on the other hand we have the acceleration caused by the system, rest of the system. That is, we could say that there are n poles in the whole system, symmetrically, mostly symmetrically, and we can take the distance d to the center of the system to be representative of the mean distance of those poles. They might be here, might be here, but let's say the resultant acceleration is something like n over d. So if we equate these two forces, or rather here it is not correct to talk about forces since we are not talking about masses, we equate these two accelerations and then we obtain a velocity that is dependent only on the total number of poles, and it's a square root of that number. So we wish to make an estimate about this velocity. So we take the earlier assumption that photons, each photon has 2 poles, so the order of magnitude of those poles in the system is also the order of magnitude of photons that we know that is somewhere like 10 to the 89th power. So this is a very crude coarse estimate, but based on this we can calculate that the velocity is 3 times 10 to the 44, and this is a plain number, but it also tells that we have a velocity that is this many unit distances of the model covered by 1 unit time. So we can then go forth and think that okay, velocity of light is 3 times 10 to the 8 meters per second. So calculating from that and fixing meters as our distance unit, and also seconds as our time unit, we get to understand that actually our unit distance, we have been talking about here the unit distance in a logarithmic potential. It is in order of magnitude 10 to the minus 36 meters. That is rather close to the Planck length, and this might be a good indicator that actually we are talking about effective model, in a sense that some observations taken from the amount of matter in the universe could be a proof in favor of this kind of model, that we obtain physics that this potential has then special behavior below the Planck distance, and we could have some kind of indications from this model how the physics is functioning in shorter distances. After having seen how we obtain light speed for a single pit, then we also must find corresponding particles to neutrinos and photon. Well, we have already said that photon is the dipole, and its zero potential internally is going here, and this orange line is depicting the universal zero potential, the 3D shell, called also 3D brane, at zero potential. And then we have also these other structures that are stable or less so. The stable one is this 2-nit 1-pit dumbbell kind of structure, whose zero potentials are actually 4 different ones. So along this line of structure, its axis, there are zero potentials here at 1.61 approximately. That is, by the way, it's the golden ratio from the central pit. And then there's also the inverse. There's a zero potential at this point and there, and on the opposite side you can find also antiparticles for these, just putting the whole structure below the brane. On the other side of it, you can find there also the same zero potential points, and there it is symmetrical. And here we have cross section going through these singularities of logarithmic potential, and we can see that actually we are not facing a singularity anywhere in these particles, even if we go at the zero distance in 3D brane, since we are only finding there a certain value of the logarithmic potential. And going along this brane, we also can find multiple potentials that are very convenient later on when we calculate something about Coulombic potential and Newtonian potential. What is interesting in this model also is that we have well, we had this one like electroneutrino. Then we have also this triangular structure where the nits are symmetrically around the central pit, and it has a situation where this acceleration impact on this nit, or any of the nits for that matter, it is acceleration attraction towards the pit is exactly overcome by the repulsion from two pits on the farther side of the aggregate. So this is a kind of indifferent equilibrium, and it means that when the oscillation of this structure is in the phase that is going outwards, the nits are going outwards from the central pits because of the repulsion at the distances shorter than unity. This expansion can go on freely, so that at some point any other pole nearby can capture one of the nits, and this 3-nit neutrino can become again a 2-nit neutrino. So this is origin of the neutrino oscillation in this model. Since we now have clear rules for attraction and repulsion, we are able to calculate what kind of secondary effects we have from aggregates that have as a basic constituent nit-pit dipole, which is depicted here to the left-hand side at right angles to the 3D brane at zero potential. So this is where the dipole within any aggregate will position itself. It's the internal potential of aggregate must have this zero value there. Then there are symmetrically many alternatives that are equivalent, but there is a kind of collapse of this aggregate into one of these positions. Usually we are talking about this dipole that is actually one of the axes of simplex, like for instance pentatope, where there are 5 positive pits here at the center, and we all have 5 negative nits, and one of those is then on the other side of the 3D brane, and the others are like radially positioned here at unity distance approximately from the pit center of the aggregate. Now what we calculate is that we have the acceleration towards a nit along the 3D brane, and we have the acceleration, attractive acceleration component towards pit, and the repulsive acceleration component away from the nit of the dipole. And since the amplitude of these accelerations is equal in strength, then we have resultant acceleration that is at right angles to the 3D brane. And since there is this right angle, it means that we have in 3D we see this point where the dipole axis perforates the 3D brane. Around that point we see a radial symmetric scalar value, and there is no vector in 3D pointing at any way, so it's kind of this vector here is pointing away from 3D. So my interpretation is that we have value of actually acceleration as reducing when one goes with nit away from this point of perforation, and that acceleration in the end it is 1 over R when we go farther away from this point of perforation. And so actually we get 1 over R for one component, but when we handle dipole, we actually get calculate, and we get 1 over R to the second, which is correct form of acceleration, Coulombic acceleration. Now, so we have in 3D spherical symmetric acceleration, and that has correct form. Now we only need to have either attractive or repulsive acceleration. So we interpret so that since this dipole has a polarity, we can switch these poles and have the resultant that is pointing the other way. Then the interpretation is that this current corresponds to the positive and negative charge coupling. So if this polarity is between two aggregates, if it remains the same, and the resultant vectors here, they point the same direction, there's a repulsion. And if the polarity between two aggregates is inverted, then this resultant is, they point at opposite directions, and there is an attraction between those aggregates. And so we have a candidate for the Coulomb interaction. It is noteworthy that when we come closer and closer to the point of perforation, to the aggregate, it is a test knit of that could belong to another aggregate. We actually don't have infinity at zero distance. So we are resolving also the problem of ultraviolet catastrophe here. Based on what was calculated in the previous slide, we get distance relation of acceleration from dipole to a nit. And we can see that value here as a blue line, and this shows that the acceleration is not going to infinity, unlike what is would be expected from a Coulomb law between in this case we are looking at positive acceleration, so this is repulsive scheme. So this is for two like signed charges. The Coulomb acceleration reference value would go to infinity. Instead, we have a value that has a distinct limit in between poles. And here we have the ratio of acceleration obtained from logarithmic potential dipole, and it is in relation to the Coulomb reference value, and we see a convergence at distance of 3 unit distances towards the practically the same value as the Coulomb acceleration. This slide is about attribution of relative strengths of Coulomb interactions to various kinds of aggregates. First, we have here as an example an aggregate where there are 3 pits at the center of the aggregate and 3 nits positions like that. We have always this kind of the bit neat dipole here. That is the connection through which our aggregate is coupled to the 3D shell, and beyond that we need a kind of coupling constant that tells us how what is the actual electric charge involved in this our aggregate. So we make a comparison to the carrier of electromagnetic interaction. So we make a comparison to a photon. On the right hand side we have the photon, and we take all the connections between the components of the dipole of the photon and components of the aggregate. And what do we discover? We discover that for this putative electron we have 9 attractive connections that are shown in green lines here, and then we have only 3 repulsive connections that are shown between nits of the aggregate and the nit of the dipole. And when we calculate the difference, so we take first the attractions and subtract the repulsions, we get a number 6. And then we also want to know if we have some other generations of particles. So we have hypothesis for both muon and tau, and the only difference is there that we have more of those negative poles, more nits around the center of the aggregate. And we always will get the same number 6, and if we are now thinking this is the electron, 6 corresponds to 1 electric charge, and so we can go forth and calculate from this point onwards also the charges for other compositions of the aggregate. The charge attribution to quarks functions more like for electrons shown earlier. So there is this relation between dipole that represents the photon and the aggregate charged aggregates. So we take the connections between photon and the aggregate to calculate the number of attractive ones. Here we have 5 of them and only 1 repulsive one. So we take this coupling so that we take the attractive ones and subtract the 1 repulsive one and get 4. And this number 4 is then related to the number 6 we obtained for the electron. So since the electron charge represents the fundamental charge E, then we have 2/3 of that charge for the up quark, and then on the right hand side we can see the down quark, and it has a calculation that produces number 2 with the same principles, and 2/6 is 1/3, so 1/3 of the elementary charge. Now the signs here are something that arise from the positioning, relative positioning of nits against pit of the aggregate, or pits of the aggregate, and we have degrees of freedom in this, both I'd say geometrically, but especially when we go to distances smaller than unity. There is also in the algebra we have options how to handle the charge, the sign of the charge, so that we obtain a correct answer here. So I challenge people to get interested in the model and see what can be done to state it in more precise terms. Anyway, what is important at this point that the coefficients are correct, and there is a possibility to handle the signs of those coefficients as well. And here we have the second generation of quarks, charm quark and strange quark, and we can see the electric charges remain the same, even if the number of connections increases, since the increase is both in attractive connections and in repulsive connections. So in that case, our charge remains the same. And finally, the third generation of quarks. We can see that the electric charge attribution still is functioning well, so we get 2/3 of the fundamental charge for the top quark and -1/3 of it to bottom quark. Also, we see that the number of nits in these aggregates is increasing, and that has an implication on the mass of the aggregate. However, we also see that while we had this neutrino that has 1 pit and 3 nits, it was already on the verge of not being a stable aggregate. In baryonic context, we can have also 1 pit and 4 nit aggregate as a participant, and because of the other pits from other quarks, the totality is remaining still stable. So these are things that are to be noted, but for this while at the moment we don't have a rigorous model for that. Also, for calculating a mass of aggregates that have less than 3 pits in the center, there is no actual mass attribution model yet. Okay, this might be a bit tricky to explain, but I'll try my best. So we calculate the acceleration imparted by the dipole to the left-hand side onto a pit here, and this acceleration converges to a Newton one very close by actually already. And so we are still interested about the second order effects of logarithmic potential and the accelerations caused by the dipole of logarithmic poles. And as we can see in the picture, attractive vectors are pointing from the pit to the right hand side towards both pit and nit of the dipole, and the resultant is something that lies then along the XYZ plane here. First we must understand the distance from dipole to the pit, that is represented by a kind of metric element, and we apply quaternions here. So we take a square of quaternion. This is kind of representative of the whole interval, it's equally valid for both A and B, and gives kind of non-directed value for the distance. And then when we want to see something value that is instead is directed, and we are looking at the point A, we wish to have kind of reference to this point A. We have to make a transformation from functions that have been produced using this kind of distance presentation. So since a dipole is calculated based on that kind of distance presentation, we obtain from there in the end minus 2r over d squared. And this is naturally not the form of function that corresponds to Newtonian acceleration. But after transformation, selecting any coordinates like x, y, and z in this plane, taking the coordinates and transforming then into a quaternion that's representing the function value seen from this point here, that is shown here. We then obtain values of a dipole that are actually the correct form. So we took this minus 2r over d squared and divided by 2r. The skew here is actually, since it's lying in the plane xyz, we can put there the distance r we had there in the acceleration function, and we obtain then the correct form of the acceleration seen from point A. So this is the minus 1 over d squared, and here it is the 4 distance still, and we can see that the difference in the next slide, that actually the convergence is far away from dipole, not even very so far. It goes towards the Newtonian one, and instead nearby we have a separate value, considering exactly this, that we are looking at 4 distance that could be also positioned this way here. So we have a finite value for the acceleration from the dipole to a pit at the distance 0, meaning distance r, so distance along the xyz plane. The details on applying these quaternionic transformations and algebra can be refined, but what's most important is that the values obtained become very reasonable respect to the present theory. So we can see here that there is this function of accelerations caused by the dipole on a pit, and this value converges towards the value of Newton acceleration reference value. It is here in dashed line, and you can see that actually already within a few unity distances we are getting the exactly the same value. And here we can see how this ratio of two approaches very quickly to unity. So we can see here that the distance of 4 unity distances, we are up to approximately, I'd say, 97% of the Newtonian acceleration, and then this means in practical terms for unity distances is in the order, still in the order of Planck distance, a multiple, perhaps a small multiple of Planck distances, and this is rather nice result, and we'll show now in the following slides how the coupling constant to this kind of basic function is obtained from aggregate structure of particles. In previous slide we saw the function as a function of distance, 3 distance from the dipole axis, and it shows the acceleration onto pit. So when we are then considering aggregates of poles, we need to have that acceleration obtained for the pit. We need to have a coupling constant to the structure of the aggregate, and it is done this way. We have connections between all the poles involved in the aggregate, so this is a combinatorics solution, and in the end we get a factorial result from it. Here we show that lines are drawn between the knit on the other side of the 3D brane, and we get these 5 lines drawn from it, and there is always there are options where whichever of these paths through the graph we are following. So here we have just one sample, so we first get to this point here, so we draw this line, and then the next line is a blue line here to the junction towards the green lines that are 3 from there at that point. So we select the one that goes to the origin of the 2 red lines, and so on. This is the way we calculate, go through the graph, and let's see what happens then. So this is one step forward. We can see that actually the endpoints are already 120, and there is still from let's see, from this last point here we go either this way or that way, and if we select, for instance, this way here, we have the last stretch to be done there to cover all the poles of the aggregate, but that is not going to multiply anymore the number of lines we are drawing. So we are getting this number 120, that is practically factorial of 5, and so since we have here 6 poles, the factorial of 5 is giving us our relative mass of electron from this model. Here we say that this is no carrier needed, standalone attribution of mass. Well, no carrier needed means that the photon is not, or any carrier particle is not essential here, but we can directly have effect on other aggregates, whichever aggregates contain a dipole in them. But it doesn't matter that the free dipoles photons are not affected, and it also might mean that since the interaction in itself is immediate in this model, it might mean that we get some effect on all the photons there are, and that they are kind of a bit affected, and there is a kind of messaging back and forth with then between these various aggregates, and well, this is all to be calculated exactly what the contribution to the gravitational pull there would be, but that's not been calculated yet in this point. This relative coupling constant for electron is then 120. We have 120 points in the end of a line here. So we have been following with these, well, we have enhanced shown kind of track of through this graph, and it is going like that. We start from the down here, go to this junction, then we go up to this junction, and then we go to that junction over there, and the red part of the track, and then finally what's remaining is only one final nit here. So we are getting this graph and have that value 120 for a 6-component aggregate. Okay, this is the listing of relative masses of various aggregates. The relative masses are obtained from factorials, and we can see that actually factorial is represented also by logarithms integral from 0 to 1, and this is exactly where these aggregates are positioned up to the unity distance from the PT center. We have the vertices of nits that are positioned in according a simplexes like a triangle, tetrahedron, and a pentatope, and their distances remain unity distance from the center of the aggregate. So okay, we first have electron, and since it's a bit kind of flat aggregate, the prediction of the mass is not very accurate. This table is fixed to a reference particle neutron. It could be equally well be fixed to the Higgs boson down here, but well, for practical purposes, I have started to calculate things from neutron outwards. So what we can see here is, well, first of all, you can see that there is this negative or positive coefficient. So I'm taking only the absolute values here, and this way I can see that going downwards from neutron, there is about 1/9 of the mass. There is the muon, and then we divide by 8, we get x17, whose composition is not, I have not a hypothesis over it. Then we can take, well, 1/7 part of that. There would be up quark quark at that mass scale, but actually I don't have a effective quark mass model under this logarithmic pole model yet, so this is just a kind of observation. And then we get to the electron mass that is very poorly correspond to the actual mass, but as I said, it's a geometrical thing that will have influence on the perceived mass when particle is probed, because by probing flat aggregate in a particle that's a flat pole aggregate in 4D, it means that the results you are getting are not representing what is the true composition of this particle. And then going upwards from neutron and proton, whose compositions are here and are actually these you can practically construct from what I have shown earlier about these quarks. Then afterwards there is this bigger mass particle that is epsilon, 10 times the neutron mass, and we have 11 times neutron mass. We have lambda kappa and sigma kappa particles. When we go beyond the unity distance from the center of this aggregate, we might get a contribution there that is null contribution on the mass, and only the successive additional pole is in a position that is falling within this range of integration. So we kind of skip one of the particles, probably because of the geometric positioning of after we have reached pentatope of nits around the pitchy center of the aggregate. And then by multiplying the mass of neutron by 11 and 12, we get practically exactly what is observed for Higgs particle. So this is kind of initial map of compositions for some of the particles we know in our present physics. And I wish to underline that this is still a model of one interaction, one potential, and one free parameter, that is the number of the poles in the system. This final slide shows structure of the proton schematically. It has the center of 5 pits that into model they are very close by each other at the center of the pentatope, and the pentatope is consisting of these 5 vertices of nits around the center, the core of pits, and we are showing just one possible route going through this graph of interactions. And this is shown on the right hand side as a ramification of possible selections for the truth, and in all there are 362,880 different ways of going through that graph. And this is the relative weight of relative mass of this aggregate, and it is fixed since we have the same number of poles also for neutron. The mass is very closely the same, but probably the exact mass is also somehow to be calculated considering some other parts of the integral of logarithm as well. These are details to be developed further, but the first version 1.0 of this model is already giving good results.